Imagine you're tasked with finding a value within a list of 10 items. That'll be quick and easy. You'll manually check each and every data point within the list from beginning to end and see if the value is there or not. What if the list goes to 1,000 items, 100,000 items, a million items? And you have to check each and every single one of them? Not so easy anymore. Classical computer uses that same approach, but with the computer brute forcing every single potential data point for a match. The method is inefficient as it takes too much time, requires too much data power for lists that are exponentially bigger in size. On average, the brute force method takes n over 2 steps, with n representing the amount of items in the list. There has to be a better way. By implementing Grover's search algorithm for the power of quantum computing, we are able to take the average amount of steps down to n square root, saving countless of hours of shifting through this data. But before we do all of that, we gotta know, what is quantum computing in the first place? Traditional computing from your laptop, your iPhone, and even your smartwatch are composed of calculations stored in binary data, or bits. These bits are either composed of either 0 or 1. Meanwhile, a quantum computer uses qubits, which acts sort of similar to bits, as they can also store binary data of 0 and 1, but they have this one special third state, known as superposition. Superposition qubits can be a combination of 0 and 1 at the exact same time. That special element allows quantum computing to have its own unique advantage over classical computing, as it can represent billions of unique states at once. But first, what is exactly Grover's search algorithm? Devised by Lowell Grover in 1999, the algorithm first gives an equal chance of probability across all outcomes, which is written as a vector. A Hadamard gate is applied to the qubits to apply superposition and prepare for the next following steps. Then, for the process called the oracle, it marks the correct solutions by changing the sign of the selected state into a negative. Now, the diffusion operator is applied, amplifying the probability vector of the selected state, which is now positive, and lowering the probability of all other states by reflecting the vector. The process of the oracle and diffusion operator, called Grover's iteration, happens numerous times. At the end, the algorithm graphs its answers with all solutions listed, and the one with the highest probability is the correct answer. To do this, it's really simple. All you need to download is Python and Qiskit. Both good tutorials in the description down below. Start our tutorial. First, we need to download our modules from Qiskit. So first, let's begin with our declared variables. For example, we'll be using 4 qubits, which are represent of a list size of 16. So the target 1001 will be the 12th place within the list with an index of 11. So for the iteration, we'll run the Grover's iteration 3 times from the formula square root of n times pi over 4, with n equaling the amount of qubits we use. And if you compute that, that's the value of pi, but we rounded it down to 3 for example. And for last off, we declare QC for our quantum circuit, and it will use n of n, which we'll use, for example, we're using n as 4, so we'll use 4 qubits and 4 bits. That's the perfect amount for superposition. So first, for each part, I broke it off into a different function. For the Grover's oracle function, we will have QC, which is our quantum circuit, and target, which is our binary number. For I bit in imaginary target, this basically breaks the our binary target apart and backwards flips it. And if the bit equals 0, so each number of it, QC.xi. That basically means that it will turn the number backward. So basically from 0 to 1. This is important because for our next step, for the phase gate change, we need it to be all 1. And this only specifically targets our target within the quantum circuit. Next, this is our phase gate. QC.append phase gate -1 control n -1 and range n. This is so that it will target our specific binary target in our qubit and phase change it of -1, which follows the Grover's algorithm. and then we redo the first step to get the number back to normal, to get the binary target back to normal, as most things in quantum computing are the inverses of each other. So this beginning one turns their target into all 1, and this second one turns it all back. Next, we'll have the Grover's diffuser, the QC. So for the QC that H range N and QC that X range N, so basically that applies the Hadamard gate and the X gate. So basically they do the exact same as this from earlier for the Grover oracle. The only difference is this is a global thing for the whole entire circuit, and this one is only dialed in for our target. So they're basically the exact same coding wise, but target wise, QC that is the exact same as this one, which applies a -1. So what will happen now is that all the target one will turn into a -1, but then we'll turn it back to normal, which is 1. But for every single other one that is not the target, before it was 1, but now it's -1, meaning all the probabilities will be lower except for our target, which will be very high. And then again, we turn it back to normal. But now, since that the probability of the target has been boosted, the things have changed of the altitude vectors. And like I said, in quantum computing, they're the inverse of each other, so it's back to normal. Once we're done with declaring all our functions and variables and whatnot, we'll actually run the circuit. Like I said before, first we declare a global Hadamard gate to prepare for superposition on our global circuit. And then we'll run Grover's iteration, which will run the Grover oracle function first, and then it will run the diffuser second, and it will run it 3 times due to our iterations amount. And at the end, we should get an example where we QCO that measure range N, that basically measures the global circuit, and we'll get our answer there. And this is just simulating stuff. Simulator that error simulator. It starts out with simulator. Result that simulator that run. Yeah. QC shots. We'll use 1,000 shots here to get the most right answer, as qubit variation can counts that result that gets the answers, and these two just display the plot. So now we'll run our code and see what plot we get. As you can see, this is all the other numbers, and we can count. There's 16 I stated earlier, and our target of 1011 is clearly the highest compared to the rest where they're lowest, meaning our circuit has worked and we have achieved the Grover's algorithm. For my next project with quantum computing, I would like to do something that has not been publicly documented online. Whatever that would be in the niche subspace within quantum computing, I would do it. I have not decided on the topic yet, but I'll try to make it a challenge, and I'll try the best that I can. So thank you for watching today's video. Be sure to like and subscribe. My name is Mindo, and thanks for watching.